the torque on any current loop then we can use the area to express it. So let's say, I mean really any current loop, let's just go ahead and do the simple one that you would first think about, which is a circle. Right? If this circle has some area A and the current's going around like that and the B field is like that, then the torque is the current times A crossed with B. That's how we get the direction of the torque, is the cross product is with the area vector. And it's that area vector we've thought about before, where it is, in this case, sticking out. You have to pick a direction you want to call positive of this area, and you say this way is out, therefore the area vector sticks out like that. So we know this is the case where the thing is going to spin. Right? We have it sitting in the plane of the board like this. It's going to feel a force out this way, a force in that way. It's going to spin along this axis. The torque is going to be up. Right? A vector across B points up, so we could draw the torque like this. And it really doesn't matter what the shape is. It could be a pentagon, a hexagon, a nonagon. It doesn't matter. Okay? If you want to find, if you have A and you want to find the direction it's going to spin, there's several right-hand rules that you can use. Okay? One is if something is feeling a torque and you want to know which way it's going to spin, put your thumb along the torque and your fingers spin. So one right-hand rule is thumb equals the torque and fingers equal the motion. If I see this situation, I know, oh, torque's that way, it's going to turn that way. We can also use this to figure out how magnetic a current loop is. So I told you early on that the magnetic field is loopy. Every time you have just a single wire, it makes a looped field around the wire. Whenever you have a current loop, it makes a field inside the loop. So how magnetic is a current loop? Let's ask that question. Sounds strange. How magnetic is a current loop? And the reason we're asking this question is a current loop is the fundamental source of magnetism. In a bar magnet, it's little atomic currents going around in a circle, things like that. So if we have a current loop, so now I'm going to draw it sort of in some perspective here. Current going around like that, A vector like that. How magnetic it is means how does it respond to a magnetic field? It's all right here in IA. So we give IA its own special name. It's called the magnetic dipole moment. So mu is I times the vector A. And there is a convention to pick the direction of A. You don't just pick which way is positive. It's again the right-hand rule. If you have your fingers go around I, then your thumb is along A. So you had another right-hand rule. Fingers are I, thumb is A. A little hard to read. But the magnetic moment, or the magnetic dipole moment, or just the magnetic moment, is sort of the fundamental thing we use to characterize something's magnetic properties.